So I'm going to review from last week, no, sorry, from Monday, antiderivatives, which is the final topic in our class. And they're called antiderivatives because they are the opposite of taking derivatives. So I could describe it like this. We have the derivative problem. Given a function f of x, find the derivative f prime of x. And what we can call the anti-derivative problem is given a function f of x, find a function capital F of x such that the derivative of f prime of x is our function. So we're given the derivative of a function and we want to find the function. And our notation is the following. The anti-derivative of f of x is written as this curly line, f of x dx, and is called the indefinite integral of f of x. So that's the important notation that we use in calculus, and a large part of what we do for the last part of the semester is learn how to compute antiderivatives, or equivalently, learn some techniques for computing integrals. So just as kind of warm up, let's make a table. Suppose I have a function f of x. I want to find the antiderivative of f of x. And then here I want to check. So for example, if the function f of x is 1, the antiderivative is x, because the derivative with respect to x is 1. If I take any power x to the n, with one exception, the antiderivative is 1 over n plus 1, x to the n plus 1. What is the exception? I can't divide by 0. So this is for n not equal to minus 1. That is n plus 1 different from 0. And again, if you differentiate 1 over n plus 1, x to the n plus 1, you get 1 over n plus 1. The derivative of x to the n plus 1, which is 1 over n plus 1. What's the derivative of x to the n plus 1? N plus 1 x to the n. The n plus 1's cancel, and we get x to the n. This is true for any power of x except minus 1. What about n equal minus 1? That's x to the minus 1, or 1 over x. The antiderivative is the natural log of x, because we learned the derivative of the natural log of x is 1 over x. And in fact, whenever you have a differentiation formula, you have a derivative formula. So the derivative of the sine is the cosine. So the antiderivative of the cosine is the sine. The derivative of the cosine is minus the sine. So the derivative of the sine is minus, the integral of the sine is minus the cosine. The derivative of e to the x is e to the x, so the integral of e to the x is e to the x. So every differentiation formula gives you an integration formula or an antiderivative formula. And that's what. And these you have to know. You don't have a piece of paper with a list on them for the exam. There are certain facts in calculus you need to know, and Among those are the formulas for basic derivatives and integrals. Okay. Now, antiderivatives, or if you like, integrals, have certain basic properties that we use all the time. First of all, we can say the following. If f of x is an antiderivative or integral of f of x, then so is f of x plus c for any constant c. And the proof is very simple. The derivative with respect to x of f of x plus c is the derivative with respect to f of x plus the derivative with respect to x of a constant of c. But the derivative of a constant is 0. So this is just the derivative of f prime of x, plus 0 for f prime of x. And if f is an antiderivative of little f, this equals little f of x. Okay, so that's one simple property. Let me just repeat what is often called the power rule. I'll use the notation of the text. The integral of x to the p dx for the power p not equal to -1 is 1 over p plus 1, x to the p plus 1 plus a constant for any constant. We have the constant multiple rule. The antiderivative or the integral of c times the function is c times the integral of the function. And we have the addition rule. The integral of the sum of two functions is the sum of the derivatives. And these are basic facts. So let me do some examples, and the more examples one does, the more homework problems you do, the more exercises you calculate, the better you will be. You really have to remember the differentiation rules. For example, the derivative of the tangent of x is secant squared x. So the integral of secant squared x is tangent x. The derivative of the arctangent of x is 1 over 1 plus x squared. So the integral of 1 over 1 plus x squared, should always add plus a constant, is arctangent x plus a constant. The derivative of arcsine of x is 1 over the square root of 1 minus x squared. So the integral of 1 over the square root of 1 minus x squared is arcsine x. I should say sometimes you have 1 over something times dx. You can also write this as the integral of just dx over the square root of 1 minus x squared. It means exactly the same thing. Okay. Any questions about that? Okay. So let's solve some problems. Let's compute the integral of something that looks horribly complicated. the integral of 4 cosine x plus sine squared x dx. So we have to simplify this because this really looks hard, and we use some basic algebra. This is a fraction, this plus this over this, so we can write this as a sum of two fractions. 4 cosine x over sine squared x plus sine squared x over sine squared x dx. So this is the sum of two integrals. It's this integral plus this integral. Here I can take the 4 outside. This is 4. This is using the constant multiple rule. Cosine x over sine squared x dx. And sine squared over sine squared is 1, the integral of 1 dx. The integral of 1 is just, let me write it over here, x plus a constant. So if you differentiate x, you get 1. But what about cosine x over sine squared x? That looks more complicated. So this is 4. Let me write it like this. This is cosine x over sine x times 1 over sine x dx, right? This is cosine over sine squared plus this, x plus c. Cosine over sine is the cotangent. 1 over the sine is the cosecant. Let me write this as cosecant x cotangent x plus c. Now, you really have to know your differentiation formulas. The derivative of the secant is secant x tangent x. The derivative of the cosecant is minus cosecant x cotangent x. So the antiderivative of cosecant x cotangent x is minus the cosecant of x plus c. And that's the answer. So I'm going to pause for a moment, and you should look at this and maybe go through it step by step. You need to be able to do the algebra that you need to do to solve this, and that's what it is. When you have complicated looking integrals, the first thing you try to do, it's not always possible, but the first thing you try to do is to simplify the problem and see if you can get a solution. Let's look at some more examples. Let me do some from the exercises in this section. This textbook has excellent exercises. So we're going to find the integral of 3u to the minus 2 minus 4u squared plus 1 du. So the variable is u instead of x, but that makes no difference. Let's use the addition rule and the constant multiple rule. This is 3 times the integral of u to the minus 2 du minus 4 times the integral of u squared du plus 1 times the integral of 1 du. And we're going to use the power rule. The integral of u to the p du is 1 over p plus 1, u to the p plus 1 plus a constant. So here, p is minus 2. So this is equal to 3. What is minus 2 plus 1? Minus 1. U to the minus 1 over minus 1. Minus 4, u squared, that's p equal 2. 2 plus 1 is 3, so u to the 3 over 3. 1 is the same as u to the 0, that's p to the 0. 0 plus 1 is 1. So this is plus u to the 1 over 1 plus a constant. So we get minus 3 u minus 1 minus 3 over u minus 4/3 u cubed plus u plus a constant. That's the answer. If you want to check on page 332, this is number 24. Let's look at number 36. Number 36 is the integral of 12t to the 8 minus t over t to the 3/2 dt. So again, using the constant multiple rule and the addition rule, I can write this as two integrals. 12, the integral of t to the 8th over t to the 3/2 dt, minus the integral of t over t to the 3/2 dt. This is 12, the integral, 8 minus 3/2 is 13/2. And t over t to the 3/2 is t to the minus 1/2. So again, I use the power rule. Here, p is equal to 13 over 2. If I add 1 to 13 over 2, I get 15 over 2 over 15 over 2. If I add 1 to minus 1/2, I get plus 1/2, plus a constant. So this is equal to 24 over 15, t to the 15/2 minus 2 t to the 1/2 plus a constant. That's the answer. So let me just pause for a moment and take a look at this. You really need to have decent skills in algebra to do these problems. How about this? Number 65. The integral of 1 plus root x over x dx. Again, write this as a sum of two fractions, 1 over x plus root x over x dx. And write this integral of a sum as a sum of the integrals. So this is the integral of 1 over x dx. And root x over x is 1 over the square root of x. So this is the integral of 1 over x dx. And this is the integral of x to the power minus 1/2. The integral of 1 over x is log x. The integral of x to the minus 1/2, again, if you add 1 to minus 1/2, you get plus 1/2. So you get x to the 1/2, or the square root of x, over 1/2, and 1 over 1/2 is 2, plus a constant. So log x plus 2 root x plus c, that's the answer. Okay. Let's look at antiderivatives in a slightly different way. Suppose we have the problem, find f of x such that f prime of x is 2x plus 10. In other words, we want to find the antiderivative of 2x plus 10. And the antiderivative of 2x is x squared. The antiderivative of 10 is 10x. So for any constant c, x squared plus 10x plus c is a function that satisfies this. Now, an expression like this is sometimes called, so this is an equation you want to solve for f of x. You're given the derivative of f and you want to find f. So this is sometimes called a differential equation. A differential equation is an equation where the unknown is a function and the equation includes the derivative of the unknown function. So if y is equal to f of x, just call f of x equal to y, then this equation is y prime equals 2x plus 10. And the differential equation problem is find y. Find a function y whose derivative is 2x plus 10. So that's an example of a differential equation. Sometimes we have some additional information or some additional conditions that we need to satisfy in our differential equation. And it might look like this. Find a function y equal f of x such that y prime, or if you like f prime of x, it's the same thing, is some function g of x and satisfies what we can call an initial condition. So we not only want to satisfy this differential equation, but at some value x equal to a, we want the value of the function to be equal to b. Okay. So that's what we want to do. So this is a differential equation with an initial condition. It's sometimes called an initial value problem. So we have a differential equation or an antiderivative we want to compute, and we want it also to satisfy some conditions. So here's some examples of initial value problems. Find a function f of x such that the derivative is x squared minus 2x, and so this is the differential equation, and the initial condition is that the value of the function 1 is equal to a third. So the first step is to find the antiderivatives of x squared minus 2x. So f of x is going to be the integral x squared minus 2x dx. The antiderivative of x squared, or the derivative of x squared, is 1/3 x cubed. So if you differentiate this, you get x squared. An antiderivative of 2x is x squared. So the general solution, or the general antiderivative of, or integral of x squared minus 2x, is 1/3 x cubed minus x squared plus any constant c. But we also want to satisfy, so must also satisfy f of 1 equals a third. What is f of 1? It's 1/3 1 cubed minus 1 squared plus c. That's a third minus 1 plus c. A third minus 1 is minus 2/3. And we want, so C minus 2/3 or minus 2/3 plus C has to equal a third. And the only, so that means C is equal to 2/3 plus a third, C equals 1. So the solution of the initial value problem, IVP, is f of x equals 1/3 x cubed minus x squared plus 1. If you plug in x equal 1, you get a third. If you differentiate, you get x squared minus 2x. So that is the winner. And again, I would urge you to just take a look at this. I'll pause for a moment. And if you have a question about any of the steps in the argument, please ask. Just unmute yourself and ask. Perfectly fine. Okay, if not, let's look at some more initial value problems. We have the initial value problem. F prime of t is 1 minus 1 over t squared. And the initial condition is that at t equal 1, f of 1 is 0. So if f prime of t is 1 minus 1 over t squared, f is the integral of 1 minus 1 over t squared dt. That's the integral of 1 dt minus the integral of 1 over t squared, or t to the minus 2 dt. The integral of 1 is t. What's the integral of t to the minus 2? If you add 1, you get minus 1. Minus 2 plus 1 is minus 1. You get t to the minus 1 over minus 1 plus a constant. So this is t minus times minus is plus 1 over t plus a constant. So f of t is going to be t plus 1 over t plus the constant for some t. But we also have this condition to satisfy. That should determine the value of the unknown constant c. So f of 1 is 1 plus 1 over 1 plus c, which is 2 plus c, and that's supposed to equal 0. So c has to equal minus 2. So the solution of the initial value problem is t plus 1 over t minus 2. You should notice that this is defined for any number t except 0. So this is the solution for all t not equal to 0. And this isn't defined at t equals 0 to begin with. It's actually very nice to try to see what these functions look like. If you just look at the function t plus 1 over t, looks kind of like this. And over here, looks like that. And it goes up or down depending on the value c. Now, these initial value problems come up when you're looking at simple mechanical problems about the motion of a particle, where you want to know is something about its position and its velocity. So here is a kind of initial value problem for velocity and position. Suppose you know the velocity of a particle. So suppose some particle moves with velocity, some function v of t, for t greater than or equal to 0, and its position is the function s of t, and we're told the initial position, the position of the particle at time t equal to 0 is some number s0. Find the equation of motion of the particle, the position function s of t. And note, what is velocity? Velocity is the rate of change, or the derivative of the position. That's the definition of velocity. If the position of the particle at time t is s of t, the velocity at time t is s prime of t. So if you're given the velocity function and you're given the initial position, this is an initial value problem. You're given the derivative of s and a particular value, an initial condition for s. So let's look at some of the examples in the text, which are very nice. If you want to follow in the text, which I encourage, this is on page 330, example 8. So runner A starts at position 0. Right? So here's the positive real axis. Runner A starts at 0 and runs with the velocity, which is getting faster and faster. The velocity at time t is 2t. So this is where A starts the race. B starts the race 8 units ahead. B starts at position, I'll use capital S, for the position of runner B. At time 0, he has a head start. He starts with, he's given a lead 8. And velocity, capital V, 2. So he runs at constant speed. So we want to find the two position functions, the position of runner A, which is little s of t, and the position of runner B, which is capital S of t, who is ahead at t equal to 6, whatever the unit of time is. So we have two initial value problems to solve. Let me just repeat them right over here. So initial value problem 1, s of 0 is 0, and the velocity, v of t, is 2t. So what is the initial value problem? The velocity, that's s prime of t. So s of t is the integral of 2t dt, which is t squared plus a constant. So s of 0 is 0 squared plus a constant, and the initial position s of 0 is 0, so c is 0. So for runner A, his or her position at time t is equal to t squared. 0 is 0 and velocity 2t. For the runner B, capital S at time 0 is 8. And the velocity is equal to 2. So that's S prime of t. So S of t is the integral of 2 dt, which is 2t plus a constant. And S of 0 is c, which is 8. That was our initial condition. So c is 8. So S of t is 2t plus 8. So at any given time, runner A is at t squared, and runner B is at 2t plus 8. And who's winning at t equals 6? Little s of 6 is 6 squared, or 36. Capital S of 6 is 2 times 6 plus 8, which is 12 plus 8 is 20. So even though the second runner starts 8 units ahead of the first runner, after 6 seconds have elapsed, runner B has moved 36 units. Runner A is at position 36. Runner B is only at position 20. So A is way ahead of B. That's the answer. Okay. Any questions about this? Okay. Then, okay, there's one more initial value problem involving position, velocity, even acceleration. So this is example 9, also on page 330. So gravity at the surface of the Earth is a force that pulls things down with a certain acceleration. Acceleration due to gravity on the surface of the Earth is minus 9.8 meters per second squared. So this is, in terms of meters and seconds, it's 9.8. In feet per second, it would be minus 32. And we know that the velocity of a particle is the derivative of the position, and the acceleration of a particle, this is the definition of acceleration. These are the different definitions of acceleration and velocity. Acceleration is a derivative or the rate of change of velocity. So in this problem, we're at the edge of a cliff, and the cliff is 100 meters high. and we toss a stone vertically upwards. So it goes up, and then gravity pulls it down, and eventually it hits the ground. So let's say the initial position of the stone, S at 0, is 100 meters up in the air. And we give it some initial velocity. The velocity at time 0, we toss it up at a speed, at a velocity of 40 meters per second. And we want to find 4 things. Find, first of all, the velocity is a function of time. B, the position is a function of time, starting at time t equals 0. The maximum height the particle reaches, and the time when it hits the ground, right? So you toss this particle up, it hits some maximum height, but gravity is pulling it down, and at a certain time it hits the ground. This is looking at the trajectory as a function of time. So how can we calculate the velocity? So we know that v prime of t, the derivative of the velocity, is the acceleration, which is minus 9.8. So we want to find the antiderivative of minus 9.8. V of t is the integral of minus 9.8, which is minus 9.8t plus a constant. And what is the constant? Well, v of 0 is c, but we're told that v at time 0, the initial velocity is 40. The constant is 40. So for our problem, the velocity v of t at any time is minus 9.8t plus 40. And of course, velocity is the derivative of the position, s prime of t. So s of t is the antiderivative of this function, minus 9.8t plus 40. And what is that? This is minus 9.8. The integral of t is t squared over 2. The integral of 40 is 40t plus a constant. So s of t is minus 4.9t squared plus 40t plus a constant. And at time 0, the initial height of the stone, you put in t equals 0, you get c, and that's equal to 100. So the position of the particle at time t is minus 4.9t squared plus 40t plus 100. So let me just write that down. So in our problem, our particle S of t at time t, its position is minus 4.9t squared plus 40t plus 100. Now, this is a quadratic polynomial in t, so it's a parabola. The leading coefficient t squared is negative, so it's opening down. At t equals 0, it's at 100. So this position, this is S, is a position as a function of time. It's a parabola. And at some point, it has a maximum height. And at some time, it hits the ground. The height is equal to 0. So maximum height, you look at the critical points of this function. What is s prime of t? It's minus 9.8 t plus 40. When is that equal to 0? That's when equal to 0, just solve for t. T is equal to 40 over 9.8. Which is 400. Oops, is that right? 400 over 98. That's a little bit bigger than 4, so approximately 4. So S at 4, I'm just going to do this very roughly. S at 4 is minus 4.9 times 4 squared plus 40 times 4 plus 100. If you use a calculator or a computer, you get this exactly. This is 40 times 4 is 160 plus 100 is 260. This is roughly 16 times 5, which is about 80. So this is roughly minus 80 plus 260, which is 180. So the maximum height is roughly 180. And if you do it more carefully with the calculator, it seems to be the answer is 182. That's the maximum height. And when does it hit the ground? When the height is 0. So S of t equals 0. What does that mean? Well, S of t was this quadratic, minus 4.9 t squared plus 40t plus 100 equals 0. The height is 0 for what value of t? You have to solve this quadratic equation. So by the quadratic formula, t is equal to minus b plus or minus the square root of b squared minus 4ac over 2a over 2a. Should be a minus sign. So this is minus 40 plus or minus the square root of 40 squared is 1600. Minus times minus is plus. 4.9 times 100 is 490. So this is minus 4 times 490 over minus 9.8. So this is minus 40. 4 times 490 is what? 1960. 1960. Yeah. So minus times minus is plus. So this is plus or minus the square root of 1600 plus 1960 over minus 9.8. If I take the minus signs, this gives me something positive, which is what it has to be. So this is 40 plus the square root of 3560 over 9.8. Let's see. This is roughly 60 squares. So this is 60, 40, 100 divided by 9.8, approximately 10 seconds. But again, if you calculate it exactly as the book does, 10.2 is to 1 decimal the correct answer. Okay. Again, this example is worked out in the book and you need to study it. Let me do a couple more examples of initial value problems. This is problems on page 332, 333. Solve the initial value problem. This is problem number 77. F prime of x equals 2x minus 3. F of 0 equals 4. So the antiderivative of 2x minus 3, that's 2 times the antiderivative of x dx, minus 3 the antiderivative of 1 2x. The derivative, the integral of x is x squared over 2, so 2 times that is x squared. Derivative of 1 is x minus 3x plus a constant. That's the general solution of the differential equation or the integral, but we want to satisfy the initial condition, f of 0 equals 4. By that x equals 0, I just get c, and that has to be equal to 4. So the solution of the initial value problem is x squared minus 3x plus 4. Right? We get a solution plus some constant just from the integral, and the initial value gives us the value of the constant. Let's look at number 81. Suppose we have a function f of u whose derivative is 4 cosine u minus sine u, and the initial condition is that f at pi over 2 is equal to 0. So f of u is the integral of 4 cosine u minus sine u du. The integral of the cosine is the sine. The integral of minus the sine is plus the cosine. So this integral is 4 times sine u plus cosine u plus a constant. If we evaluate this at pi over 2, this is 4 times the sine of pi over 2 plus the cosine of pi over 2 plus a constant. But the sine of pi over 2 is 1, and the cosine of pi over 2 is 0. So this is 4 plus c, and we want that to be equal to 0. So c has to be minus 4. So the solution of the initial value problem is f of x equals 4 sine u plus cosine u minus 4. All right. Let's see. Let's continue to think about antiderivatives and integrals. But I want to introduce a problem which looks a little bit different. But we'll come down to just finding integrals or antiderivatives. So this is the problem of finding area under a curve. So for example, suppose you have the function y equals, say y equals x. And we want to find the area between the curve and the x-axis, let's say for x between 0 and 3. So here's the curve y equals x, just a straight line. Here's the x-axis. And between 0 and 3, it's a triangle. So we don't need calculus for this. The area is a half the base times the height, which is 9/2. Suppose we ask the same problem now, but instead of x between 0 and 3, for x between 1 and 5. So we have exactly the same problem, 0 to 5, 0 to 5. For x equal to 1, that's here, x equal 5 is here. So the area under the curve from 1 to 5 is this. It's a trapezoid. And again, you can get the area. It's it's not the area of a triangle because it's not a triangle. It's not the area of a rectangle because it's not a rectangle, but it has a horizontal base and two sides. This is 1 high and this is 5 high. So the formula for the area of a triangle, the area of a trapezoid, is the base times the average of the heights of the sides. So the base is 4, and the height is 1 plus 5 over 2. That's 4 times 3. This is 12. Well, that's not so hard. Suppose I take a unit circle. So the circle is x squared plus y squared equals 1. Suppose I'm just interested in the area of this quadrant of the circle. I mean, I could describe this curve by a function. If I solve for y squared is 1 minus x squared. So y is plus or minus the square root of 1 minus x squared. And I take the plus sign if I want the top half of the curve for x between 0 and 1. So from 0 to 1, here's the curve y equal 1 minus x squared. That looks like a complicated function, but of course I don't need that to find the area. The area of a circle of radius 1 is pi, and this shaded part is 1/4 of it, so that area is just pi over 4. All right, so I just found the areas of some regions. Let's take one more example of a function which comes up often in beginning math, like parabola. Suppose I take y equal x squared. Now, it's not a particularly good drawing, but let's say that's my parabola. And if I look at the region under the parabola for x between 0 and 1, that's this area. Very easy to draw, very easy to graph, but find the area. And that's a problem that you never learned how to do in geometry. And we need calculus to solve that problem. So it turns out one important application of antiderivatives or the integral is to find the area under a curve, or the area between the negative or between the x-axis and a curve for some values from a to b. So we have what we might call the general area problem. Given a function f of x, compute the area between the curve y equals f of x and the x-axis for x between a and b. So here we have some curve y equals f of x. And this is say x equal a and x equal b. And we want to find this area. So I'm going to talk about this in much more detail next week, but just so you're familiar with the end of the process, that is the answer. The answer is the following, and it's quite beautiful. Suppose we let f of x, capital F of x, be the integral of f of x dx. Then this area under the curve, A, is going to be this antiderivative of the integral evaluated at B minus the integral evaluated at A. That's like this amazing formula that connects a completely new problem, area under a curve, with what we've been talking about in different contexts, derivatives and antiderivatives. And let me just, as an example, show you that this works for the problems we've been looking at. So suppose I took y equals f of x equal to x. So I wanted to find the area of this trapezoid. So capital F of x, which is the integral of little f of x dx, that's the integral of x dx, which is a half x squared plus a constant. And so if I want to calculate f at some number b minus f of some number a, that's going to be a half b squared plus a constant minus a half a squared plus a constant. The constants cancel, so I could just take the constant equal to 0. That's a half b squared minus a squared. A half b squared minus half a squared is a half b squared minus a squared. Huh. So what do I learn from that? Well, if a is equal to 1 and b is equal to 5, the area is a half 5 squared minus 1 squared. It's a half. 25 minus 1, that's 24 over 2. That's 12. Huh. What did I get before when I did it just using baby geometry? The area of the trapezoid was 12. So that works. Suppose I want to solve my problem about the parabola. Here's the curve y equal x squared. I want to find the area under the parabola from 0 to 1. That's really a hard problem. I don't think the Greeks could have solved that when they were inventing geometry. So I have the function f of x equals x squared. The derivative or the integral of x squared dx is the third x cubed. I'll take c equal constant, c equals 0. So a third x cubed. So the area is going to be f of 1 minus f of 0. The area under the parabola y equal x squared from 0 to 1. F of 1 is a third 1 cubed. F of 0 is a 1/3 0 cubed. That's a third minus 0. It's a third. So now this is actually a miraculous fact. 1/3. That's the area under this parabola from 0 to 1. I mean, really, it's quite fascinating. If we had taken the triangle, this triangle, that's a triangle whose base is 1, height is 1. So we have angle area half. But this parabolic region, that has area third, which actually means if we wanted to subtract this sort of like moon type area, that would have to have area, this plus this equals a half. So that would be a sixth. So using the integral, we find these quite lovely formulas for areas of very naturally defined geometrical objects. Huh, that's cool. So that's sort of a hint of coming attractions. This is the last topic in our course, is using integrals to compute areas and similar problems. Of course, I have to justify this, as I haven't explained why the integral somehow is connected to area, but that is coming attractions for next week. I want to just remind you, though, of one important thing. The second midterm 2, is almost 2 weeks from now, Monday, May 1, 11 o'clock in Gillette Hall on campus, Gillette 205. So got to be there. All right, that's all we're going to do today. Any questions before we quit for the morning or early afternoon, I guess? Okay, thank you. Be well, enjoy the lovely weather. See you Monday morning.